All right, good morning, everybody. We're going to start the next unit of material here as my dog plays with a Coke bottle in the background. We're going to start our next unit of material here talking about DC circuits. So now we're going to move away from this idea of electrostatics, and we're going to start talking about current flow. So as we look at a circuit, a lot of people perceive circuits to be these very mysterious things when really they're pretty straightforward, at least in the basic understanding of how they work. Now, don't get me wrong, I'm not going to try to wire my house or repair anything electrical. I'm going to call somebody to do that, but at least having an understanding of how things work will be beneficial to us because electrical circuits and current flow shows up in a lot of places that you might not expect. So we're going to take this idea of charges, and we had this buildup of charges on the capacitor. And when we discharged that capacitor, what we got was a temporary state of current flow. So when we look at charges in motion, we say that that's current. So while the capacitors are discharging or charging, charges are flowing. So current is flowing, but then it stops once the thing becomes fully charged or discharged. Now we're going to look at a situation where the current flow is continuous. So when we have a battery connected to a circuit, what it does is it supplies an indefinite supply, or more or less in the moment, an indefinite supply of current. Or when we plug into a wall, we have an indefinite supply of current or charges, so we can maintain this current flow. So now we have to have an electric field. Remember, in the last unit, we said we did not want an electric field in our capacitor or in our circuit or in our conductor because we wanted the charges to stay still. Now we absolutely need one because we want the charges to move. So what happens is when you flip a switch, you're not really opening a starting gate for charge flow. What you're doing is you're establishing an electric field. And there's already charges all throughout that piece of wire or that conducting thing. And when you establish that electric field, they immediately begin to move. Now, a lot of people think what happens when you flip a switch, again, it's like a starting gate for charges. And those charges that have been waiting there patiently at the switch rush through the circuit to the light. And that's not how that works. If that were true, it would take minutes before that light came on in some cases. So what really is happening is there are charges in that piece of wiring that are already right by that electrical fixture or that light or whatever it is. And when you establish that electric field, it's those charges that are already right there at the object to begin to drift or move into the piece of, electrical equipment or whatever it is. So there's this mass motion of charges that's actually quite slow. It's a lot, I say it's a lot like people trying to get down a busy aisle at a grocery store or at a Walmart or something. Think about the school supply aisle or the Halloween costume aisle or something when it's really busy and you have to kind of pick your way through. That's essentially what these electrons are having to do because there are so many of them. Now they're mostly generally moving along the direction of the field lines, but there is some random motion. And the way we know there is these wires will get hot. This random motion will create heat in the conductor. We call that random motion the drift velocity, and it's actually only a few centimeters a second. It's not very high. That is the mass motion or the bulk motion of these electrons through the circuit. So it has to do with the number of electrons you have, so the conductivity. It has to do with the area that they have to move through. So think a larger area means more motion. And it also has to do with the distance they have to travel, the distance that they have to travel through the conductor, all right? So the larger area means less interaction with each other, but the longer distance means more interaction. And the type of material it is determines how many electrons there are. So these three things together are going to determine something called the resistance of the wire. And the resistance is a measure of how easy it is for current to flow through the circuit. Again, the harder it is for current to flow through that circuit or the higher the resistance, the more heating we get. And heating, you know, all electrical conductors lose some of their energy to this random motion heating, but some things are better conductors than others. Also, the amount of current flow determines how much heating there is. That's why we have safety things like breakers and fuses and stuff like that to prevent there from being too much current flow, causing too much heating and melting the insulation or causing a fire. Now, this drift velocity is determined by the field strength, okay? So we've established the field, and in your house is wired to have a certain electrical potential or a potential difference, and then that's what establishes the electric field when you switch something on or off or plug something in. Okay, so if we need a large current, we need usually a heavier gauge wire. So if you think about, say, for example, extension cords, you can buy a little El Cheapo extension cord at the store for a couple bucks, maybe even for $1 at the dollar store. That is not going to work to run a piece of major electrical equipment. It's going to burn it up. So if you want to run, say, some heavy duty electrical equipment or some large tools or something, you need a contractor grade extension cord, which are generally significantly more expensive because if you look at the wire inside there, it's much, much larger in diameter. We say it has a gauge difference, okay? The lower the number, the bigger the wire. So the lower the number, the larger gauge that thing has, and that will pass more current. So all of these things go together to create something called the resistivity, all right? The resistivity is, or the resistivity is a property of the material. So let's say I'm going to use copper, I'm going to use silver, I'm going to use gold if I'm really wealthy, okay? Those things have different conductivities, so the resistivity of them to current flow is different, all right? It turns out that silver is a better conductor than copper and gold is better than silver, but gold is really expensive. So when you look at the wire, the current flows through the wire based on the electric field, but also the length and the area. And remember, we're going to talk about something called conventional current. Conventional current is actually the opposite direction that electrons would flow. We call it the positives or the holes are flowing in the direction of the conventional current, which means the electrons are going the opposite direction. So we're going to assume we're going to assume current flows with the field lines. And we know from the last unit that's not true. Electrons go the opposite way, but we're going to say current flows with the field lines or it flows downhill for the electric field. So what we do is we take this idea and we look at the relationship between current and potential difference and put that together with resistivity, and we measure that with something called Ohm's law. So to find the resistance or how hard or easy it is for the current to flow through something, when we build that object, we determine its resistance. All right, so we build it out of copper wire, we make it a certain length, we have a certain gauge of wire, we put all those things together, and that gives us the resistance to the current flow. So the resistance is equal to the rho, which is the resistivity, which you look up in a book, times the length of the piece of wire that we're using, divided by the cross-sectional area. Most of the time, wire is circular, so it would be the cross-sectional area of a circle, or the area of a circle would be our area. And all those three things together determine the resistance for that particular electrical component. Now, if you put these things together in something called Ohm's law, what we find out is there is a direct relationship between current, resistance, and potential difference, okay? So the potential difference, now we're going to switch over and start calling it voltage, all right, because that's the standard terminology for it in most electrical current applications. It is directly proportional to the product of the current times the resistance, all right? So as the current or as the potential difference increases, if I keep the same electrical component, I'm going to increase my current flow, okay? Or as the resistance decreases, for example, the current flow will increase, because the voltage would have to stay constant if you were plugged into something. Okay, now the nice thing about Ohm's law for things that are purely resistive, in other words, they are based on that formula we saw for resistance, you can look at the circuit all together, or you can look at branches of the circuit, or you can look at individual components, and Ohm's law will work all the time. So you can use Ohm's law to break a circuit down into parts to analyze it. Now, we build these things called resistors, okay? If you open up something electrical, somewhere in there, there's going to be these little things that look like tiny little, you know, rolls or tiny little cylinders, and they have colored stripes on them. And these things are the resistors. They are used to split current up or move current around or something like that. They allow that current to be used in different parts of that electrical device, or split up or moved or whatever. So because they're usually very small, they use a color code to tell you what color something is. So sometimes we just have pure resistors, like a toaster or an incandescent light bulb. Their resistors are not wrapped up because there's what we use. You know, the zigzaggy wire inside a toaster is essentially a giant resistor that is, we're taking advantage of this ohmic heating to heat up the wire to make it glow to cook our toast. Okay, but most of the time the resistors are packaged in something because we don't want to use that heating because it'll damage whatever we're talking about. Now, there's other things that can also resist current, but they're not what we call ohmic. They don't obey Ohm's law. Things like capacitors, which we already talked about. There's things called diodes, which we know as LEDs, light emitting diodes, or things called inductors that we'll see when we talk about magnetism. These things also provide a resistance to current flow, but they don't obey Ohm's law. They don't go as V equals I times R. They have different formulas to calculate the current flow through them. Okay, we're going to spend quite a bit of time talking about circuit analysis. So I'm going to do a whole separate video just on that with my iPad so we can draw pictures. But the basics of current flow in a circuit is you've got to have a complete loop. You've got to shut the switch, you've got to make a connection, whatever, to maintain the current flow. Then the current flow is always going to flow in the direction of decreasing electrical potential energy. Remember, we talked about that in Unit 2. That's always the case. For this case, it's going to be flowing in the direction of decreasing potential, so to the more negative side, because we're talking about conventional current, which we call a positive. But in a circuit, we have to return the charge to the same point that it started. So like, think about a water feature in your garden. If you had a nice little waterfall and you had water at the top of it and you turned it on and the water flowed down, if you don't have a pump of some kind to recirculate that water, your water feature is not going to be very exciting for very long. So we need the equivalent of that in this circuit to be able to pump the charges back up and let them flow through again. And that's the job of a battery. So the battery is the potential pump, which increases the electrical potential energy. So when we let things go, they flow naturally downhill, but now I need to have something that'll push them back up the hill so that we can recirculate them. So in a circuit, there's two ways to look at voltage. There's the ideal voltage, or something we call the EMF, or the electromotive force, which is a terrible name because it's not a force, it's a voltage. And then there's the terminal voltage. So when you buy a battery and it says it's a 9-volt battery, if you were to actually measure the voltage across it while it was being used, it would be less than 9 volts because the battery has some internal resistance to its own current flow. That's called the internal resistance. It is dependent upon what the battery is made out of, but also how much current flow you're trying to get out of it. And so the actual voltage you get out is less than the ideal voltage. So in the ideal world, the terminal voltage, or VAB, what you get when you measure across the battery, is actually equal to the total voltage, or what we call the EMF. But in the real world, they're usually less. There's usually a little bit subtracted off of them because of the current flow and the internal resistance of the battery. So the second term in this picture shows you that that term that's determined by the internal resistance of the battery. But the EMF is the idealized voltage. So sometimes it'll say ideal battery, which means you get to use all of it. And then if it doesn't, it'll tell you what the terminal voltage is, or it'll tell you how to figure it out. Now, We only have to worry about this when there's current flow. So if I take my battery out of the package and I just measure across its terminals, it'll be 9 volts because I'm not drawing any current out of that thing. So when I put it on a load or have a load resistance on it, like a light or a radio or whatever I'm turning it on, using to turn on with, then I lose some voltage. Then I have my terminal voltage being less. We measure these things with meters. Now there's two ways that there's two kinds of meters we're going to talk about, and we're going to hook them up in the circuit in different ways. All right. We're going to consider ideal meters that don't affect our system. And we're going to talk about the ways we hook these up when we look at circuit analysis a little bit more. So I'm just going to mention it here, and then in the next video, I'll show you how we do that. Voltmeters are across something. You want to measure the voltage across the terminals or across the two ends of something. So in an ideal system, those voltmeters don't affect the system, so they don't pass any current, meaning that when I put them across there, I don't want to open up a new channel for the current flow to happen. So I have to have a voltmeter that has a huge resistance, has almost an infinite resistance. An ideal meter would be infinitely high. In the really real world, they're pretty close to that. So they don't draw any current. They don't split the current up. The current will just continue to go through the circuit as normal. The opposite of that is an ammeter. An ammeter needs to be connected in line with the circuit because you're measuring current flow through something. So you want the current to flow through the meter. In that case, you don't want to drop any voltage. You don't want to affect the voltage of the system. So you want the ammeter to act like it's zero resistance. All right. So voltmeters are very high resistance. Ammeters are zero. And that's why when we do circuit analysis, you have to be careful how you hook your ammeter up because you can actually burn it up by hooking it up wrong and passing a lot of current fluid through it and burning up the elements inside. Okay, so when we talk about circuit analysis, I'll show you more of these. So we call connecting across, we call that parallel, and we can all connecting in line series, and you'll see that in the next video. So that's where I'm going to stop this video, and in the next video, we'll pick up circuit analysis.